For this example, we have that the results of a state math test for random samples of students taught by 2 different teachers at the same school are shown below, where we have means of 473 and 549, standard deviations of 39.7 and 24.5, and sample sizes of 8 and 18, where note that these are all sample measurements. And we want to see if we can conclude that there is a difference in the mean math scores for the students of the 2 teachers, where we're letting alpha equal 10%, 0.10, and assume that the populations are normally distributed and the variances for them are not equal. So here, when we're trying to verify our conditions, we want to go through this a little more carefully this time than the previous ones, because for one, we have a bit more room for variance, ha ha ha. And also, because there's a little bit more detail to chase around in this case. So the first thing we want to do is think about whether or not for sure this is going to be an independent test that we're running here, because obviously we're running it with 2 samples, so at least we know we're in the right chapter. And this is independent because we're dealing with the students of 2 completely separate teachers, not one teacher before doing something and that same teacher after doing, say, a pretest. But more obviously, we can see that one sample is 8 students and the other sample is 18. That is much smaller. So, because they're different sizes, they cannot possibly be paired, they cannot possibly be dependent, so they are independent, and we're also not given any information about the populations at all, really. So, this has to be a 2-sample t-test for independent means without sigma 1 and sigma 2. Like I said, it's still a mouthful, where the last thing we want to check is whether or not this will be pooled, and in this case, we are told that we do not assume the variances are equal, so they are not pooled. We're using the nicer form, in my opinion, the more reasonable form, in my opinion. And then also, just to be sure, because these are assumedly normal populations that we're dealing with. I don't know why I blanked on that phrasing so badly, but whatever, it happens. Because we're assuming normality, the central limit theorem holds. I'm not going to track it. Just be mean, not helpful. Anyway, our conditions work. So from there we want to talk about this in terms of our hypotheses and our claim, where that follows a very similar pattern. It's just, well, we're in more of a comparative mood. In particular, what we're looking for is whether or not there's any difference. So, one of our hypotheses, the one that we are claiming, is that mu1 is different from mu2. Mu1 can be bigger, mu1 can be smaller. And remember here, we're not saying that mu1 is bigger or smaller than a specific thing, we're saying that it's bigger or smaller than a other value, a different parameter for a different population. In this case, either teacher 1 has higher scores or teacher 1 has lower scores. And the opposite of that is that they are equal. That fundamentally they're the same, even if they're not exactly the same, they're close enough that the difference isn't noticeable. Where this has the flavor of a null hypothesis, and our claim has the flavor of an alternative. Then from there, if we want to get our level of significance, something we're given, something we're told, usually in that last sentence of the problem statement, here alpha is 10%, and because we are looking for any difference, not one specific side or the other, this will be a 2-tailed test. So hopefully, these setup steps still look very familiar. From this point on, things take a bit of a different tone. They have some different things we have to pay attention to. For the purposes of this example, I'm going to use the critical value approach, but I'll still try and build in some of the p-value details as well, just so we know that they're there and we know that they're doing the same sort of thing as they would be otherwise. But if we're going to use the critical value approach, the next thing we need to be sure are our degrees of freedom, where in this case, it is important to pay attention to that detail that we are not running pooled samples. Because we are not running pooled samples, when we are going to get our degrees of freedom, we pick the smaller sample size. In this case, that ends up being n1 minus 1. So here our degrees of freedom are 7. If we dealt with the pooled samples, we'd add them up and subtract 2, but we're not, so that's what we do instead. Once we have that, we can talk about our critical values and rejection region. For our critical values, whether you want to use a table, the tables actually get better the further we go on here, or what I prefer is the calculator. If you're going to use the calculator, that's going to be something in the flavor of an inverse t, where because we have 10% split between two tails, that's 5% with that value 7 degrees of freedom, which will give us, be sure, plus or minus inverse t. Anyway, that will give us critical values of positive or negative 1.895. So our rejection regions will be above 1.895, that is greater than or equal to 1.895, and below negative 1.895. So smaller than, less than or equal to negative 1.895. Those are our rejections, and then from there, once we have our critical values and rejection regions, then we can do some test statistic flavored things. We can finally use this fancy formula. So, not the very prettiest formula to work with, as you may see, although it's not too far away from things we've done before. Where here, because we're working with the unpooled version, we don't have to deal with that sigma hat character, thankfully. So our formula is just x bar 1 minus x bar 2 minus mu 1 minus mu 2 over, oh boy, the square root of s1 squared over n1 plus s2 squared over n2, and I don't quite have enough space here now to include this in the way that I want to with all of these numbers written in, but we do have the numbers there. Now it's going to go where? We're going to have that 473 minus 459. Like I said, we're kind of assuming that these are the same, so that difference is going to be 0. And then down here, we're going to throw a bunch of nasty little pieces into a radical, and what we should end up with is something approximately equal to 0.922. So, with this in mind, with our critical values and rejection regions in mind, we can make something like a distribution around which we can finalize our decision. So we'll have a piece something like so, where we can see that based on the position of our test statistic, our position of our test statistic in particular relative to our critical values, it is in between them. That is, it is in the non-critical or non-rejection region. And as a result, we would fail to reject our null hypothesis. We would not reject the statement that these two are equal, even though technically speaking, they're not the same. It's just that for our purposes, they're close enough that we think that can come down to random chance. That it's not quite enough to say that there's something definitely incorrect about that assumption anyway. So, in other words, because our test statistic is between the critical values, we fail to reject the null hypothesis. And then, if we want to get our conclusion off of this, we could say something to the effect of, there is not enough evidence for alpha equals 10% to support the claim that the mean math test scores for the students of the two teachers are different. Now, when we're dealing with this problem, Working on that side of things is a little bit nasty, and it's a little bit of work in and of itself. Really, what I would recommend doing instead of going through these pieces in this way is to get used to the two-sample t-test instead, where if you run through the two-sample t-test, what you'd end up with, like before, is a p-value, where you would get that that p-value is bigger than alpha. P is large, so you would not reject the null hypothesis. Much in the same reason. Again, steps are a little different, inputs a little different, but follows a very similar process, gets to a very similar result. Anyway, this is one example for how we can do this using critical values and an unpooled sample. So, leaves us with a little bit that we can talk about for one more example.